This is one of the videos in which I try to put some aspects of power systems, where I am an expert, into music where I am no expert at all. So let me first tell the facts about grid hum and grid frequency. As you might know, the European electricity grids use alternating current with a frequency of 50 Hz. In North America and in parts of South America 60 Hz, but let's stay with our familiar 50 Hz frequency. This frequency lies within the range that is audible for human beings. But can we actually hear the grid frequency? Our ear is sensitive to pressure variations of the air, not for the electric and magnetic fields which are produced by power installations. But maybe an audio amplifier picks up some of the electric or magnetic fields. It should not, but if it does, the 50 Hz voltage may reach the loudspeaker or the headphone and become audible. If, for example, a damaged cable is connected to an amplifier's input socket, the 50 Hz signal may be too strong to be processed properly. The amplifier will then overmodulate, which turns the 50 Hz sine shape into a 50 Hz rectangular shape. But often you can hear the grid frequency even without an audio amplifier. Transformers or chokes that are connected to the grid contain ferromagnetic cores made of iron. These are subject to a physical phenomenon which is called magnetostriction. Magnetostriction means that the material contracts under the influence of a magnetic field. But the contraction is not directly proportional to the magnetic flux in the material, but proportional to its square. Thus, the 50 Hz sine shape of the magnetic flux causes a sine shape vibration of double frequency, that is 100 Hz. But the frequency doubling due to magnetostriction while keeping the sine shape is a simplification. In reality, the construction of the transformers and chokes will cause nonlinearities, and these will lead to deviations from the sine shape. This will be important when we move on to the question whether frequency fluctuations can be audible. Although reality is more complicated than that, I chose a 100 Hz triangle-shaped vibration as an example of the resulting sound. Now, the grid frequency is kept very constant in a power system, however, there are slight fluctuations. If, momentarily, more energy is produced than consumed, then all synchronous generators in a power system will slightly accelerate, and if vice versa less energy is produced than consumed, then they will decelerate. Of course, this leads also to a change in grid frequency, and in terms of an audible tone, this means higher or lower tone pitch. So the question arises, would that change in the tone pitch be audible or not? Well, the human ear is quite sensitive to changes in tone pitch, but not for sine waves with frequencies as low as 50 Hz. But we already saw that the grid hum will very probably be distorted and thus deviates from the sine shape. This makes frequency fluctuations better audible. However, the public grid is so stable that frequency fluctuations normally remain inaudible. But there are exceptions. As students, we could visit a converter station of the Russian railway in Switzerland, and there we could clearly hear the fluctuating speed of the synchronous generators. This is an isolated, relatively weak grid, and in such cases the frequency can vary enough to become audible. A bit overdone, and using again our triangle-shaped waveform, it may sound like that. Fluctuations of the grid frequency are also part of my teachings in electric power systems. And for my script, I invented a fictional character called Winga. I described her as being the lead singer of a rock band, as being fascinated by what I told about the frequency fluctuations at the Russian railway, and as considering to write a song for her band on this topic. Now, since a fictional person cannot write songs, I wrote and sang a fragment myself. Maybe it can be used as a refrain should the song eventually be completed.